Okay. Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Today I would like to continue our lesson in topic number 2, stiffness method analysis. Okay, this time I would like to explain to you how to analyze beam using stiffness method. Okay, let's see it together. Okay, class. Okay, so before we move further, okay, let's revise back the learning outcome for analysis of beam using stiffness method. Okay, number one, at the end of this session, you should be able to define the stiffness matrix for beam, identify the constraint and unconstrained degree of freedom for beam, convert the intermediate loading to equivalent nodal forces, formulate the member stiffness matrices or element global stiffness matrices, and assembly the stiffness matrix for the beam structure. And last is determine the unknown nodal displacement or nodal deformation, support reaction or unknown reaction forces, as well as internal forces. Okay, why we need to study stiffness method? Stiffness method actually is the theory behind all structural engineering software. Okay, so it provides a very systematic way of analyzing determinate and indeterminate structure. So this is the advantage of having stiffness method or using stiffness method to analyze structure, because we can use this to analyze both determinate as well as indeterminate structure. Okay, compared to the flexibility method, we will use that method to analyze only indeterminate structure. Okay, so but for stiffness method, we can use to analyze both determinate and indeterminate structure. Okay, what is another advantage? Okay, in stiffness method, we need to express force displacement relationship in terms of unknown member displacement. So we will use the stiffness method, and by using force displacement relationship, we will determine the displacement. Okay, using equilibrium of assembled member, we will find the displacement or the unknown displacement in analysis of beam using stiffness method. Okay, we also call as non-zero degree of freedom. Non-zero degree of freedom, because zero degree of freedom itself, degree of freedom. Okay, in degree of freedom, we have to understand two terms. One is unconstrained, another one is constraint. Constraint means supports. So whenever uh, system have support, there is no displacement. It means that no displacement means zero displacement. So in other condition, okay, in other condition or in opposite condition, there are non-zero degree of freedom. Okay, so in this stiffness method, we have a coefficient of unknown stiffness coefficient. Okay, for flexibility, we have the flexibility coefficient. So in stiffness method, we have the coefficient and it called as stiffness coefficient. Okay, okay, next advantage, they are directly give the desired displacement. Okay, using stiffness method, this is advantage. This is the advantage, another advantage, where by using stiffness method, we can get both displacement and reaction directly using one analysis. Using one analysis. Okay, but by using flexibility method, we can only determine reaction. or internal forces using flexibility method, but we cannot determine displacement directly. Okay, we cannot determine displacement directly. If we want to determine displacement, okay, displacement, we need to apply a unit load method. We have to put a unit value, okay, at which position that we want to calculate displacement, and then we have to apply the virtual system. Then we can calculate the displacement one at one time. Okay, but by using stiffness method, we can get displacement and reaction at each nodes directly. Okay, so actually stiffness method is easy to apply in a computer. As I mentioned just now, this is actually the theory behind all structural engineering software. Okay, let's look at next. Okay, the basic concept. So I hope until this stage you have understand the meaning of nodes, the meaning of element. Okay, so as revision, node is actually represent by number. Okay, it is actually join. Okay, join, but in stiffness method we use number to represent nodes. We use number to represent nodes because this is the theory behind software. And in software we normally design for design the building. For example, we may have so many nodes, nodes number. It may be 1,000 nodes. So we cannot use the ABC, okay, in the software because it has limitation. But by using numbering to represent nodes, okay, it will be better. It will be suitable for the software to analyze or to model the structure. Okay. Uh, Element, what is element? So if conventionally you have learned under the solid mechanic and under determinate structure subject, okay, the word element, the word member AB, member BC, okay, member AB, member BC, but this time, okay, we use element. Okay. Okay, same as this is the reason of using element. We use element number. The reason of using number is the same reason with why we use node number. Okay, it because when we use number, it has no limitation. When we model the structure in the software, we may have 1,000 elements. Okay, so next. Okay, so degree of freedom. Degree of freedom. So what do you understand about degree of freedom? Okay, degree of freedom in simple word. Degree of freedom means displacement component. Displacement component in simple words. Okay, it means number of possible direction that displacement or forces at a node can exist in. It means it free to move, okay, and it will be depend on support condition. And for beam, we will consider two degree of freedom in y and z direction. In y and z direction, because x where it represent the axial deformation or axial force, there is no value. There is no value. When we have, for example, cantilever beam, when we have, for example, cantilever beam, this value will get zero all the time. Okay, all the time we'll get zero. That is why the reason why we don't have to consider this in in beam. So in beam, please remember we have to consider two degree of freedom in y direction and in in y direction and in z direction, rotation. Okay, y and z, and it always, okay, it always in this direction. This direction, we have to refer to this direction as the sign convention for beam analysis using stiffness method. Okay, Y is going up whereas Z is counterclockwise. Okay, next. Okay, let's look at the characteristic of degree of freedom. Okay, as I mentioned previously, we have to look at to the degree of freedom in unconstrained system as well as constrained system. In simple way, we have to refer to the support system. For example, we have to look at to the pin support, the fixed support, and roller support, and it is actually constrained in the system. Okay, and in the beam system, whenever there is a support, means that there is no displacement. Displacement is equal to zero. Okay, let's look at the characteristic. Have support. Constraint means support. What is the other criteria? Displacement is equal to zero. So logically, when there is a support, there is no movement. Okay, displacement is equal to zero means zero displacement. Zero displacement. And logically, when there is a support, there are unknown reaction, at the support. So there are four characteristics of constraint degree of freedom system. Okay, let's look at to the unconstrained degree of freedom system. So the condition of unconstrained degree of freedom system, or the characteristic of degree of freedom system, is opposite with constrained system. If the other one, for example, have support, the other one must no support. Okay, if in constraint displacement is equal to zero, in unconstrained displacement is not equal to zero. Okay, when in constraint there is zero displacement. Okay, the other one is non-zero displacement or unknown displacement. Zero or non-zero. Non-zero. Non-zero means unknown displacement. Logically, when at any position or at any nodes, when there is no support, means it can move. When it can move means there is a displacement. What is the value? We do not know yet until we calculate the value. So displacement is actually the first outcome, or the first objective when we calculate or when we analyze beam using stiffness method. So, and the last characteristic is in unconstrained system, there are known forces. Okay, known forces. It is because in constrained system, unknown reaction. So the opposite with unknown is known forces. Means that we have to put the value of forces into the force displacement equation. Okay, before we can analyze the value of unknown displacement. Okay, so let's move to the next slide. Okay, the next term, or the next concept that you need to understand is boundary condition. Boundary condition. What is the meaning of boundary condition? Okay, why I introduce you to the term of boundary condition? Actually, in the software, you will see this term. Okay, the boundary condition. So what is actually boundary condition? Boundary condition is constraint or support. Okay, support. Okay, so there are three types of support. There are fixed support, pin support, and roller support. And in analysis of beam using stiffness method, we actually have two coordinate system. We have local as well as global system. But in the analysis, we can straight away use the global system to analyze the unknown displacement as well as unknown reaction. Okay, so next. Okay, member and node identification, what does it mean? Actually, in the analysis of beam using stiffness method, or analysis of structure using stiffness method, what we need to understand is we get the structure. You are given the structure and you need to analyze the structure. So you need to analyze the structure. So what actually we do when we want to analyze the structure is we will divide the structure into element, because structure is come from element. If we okay, structure, okay, we go backward. Structure is actually combination of many element. Combination of many element produce structure. So what is actually element? Element, element come from nodes. Element come from nodes, two nodes. This one is many. Okay, structure come from many elements, and one element come from two nodes. Okay, so in order to analyze structure, we must start from nodes. We must start from nodes. So what we actually do in the analysis is we subdivide the beam or the structure into element. Okay, into element. But we must understand that we must apply all the characteristic, including the cross-section area, the material properties, we need to include into the analysis. Okay, the nodes of each element are located. The nodes of each element are located at a support or at point where members are connected together. So this is how we identify nodes in the system. Okay, other than that, where an external force is applied, then also we can put as nodes. Or where the cross-sectional area suddenly changes. For example, if one beam, okay, have this and this, okay, this, for example, okay, let's say A, we have A, B, C. Okay, the first part from A to B is actually 3 EI. But from B to C, we have 2 EI. So that what the statement means. Means that we have to we cannot assume that AC is one element. We have to divide into two elements due to the changes in the cross-sectional area. Okay, and another one is where the vertical or rotational displacement at the point is to be determined. Okay, okay, so we move to this. Okay, let's look at to the figure number 1. Okay, figure number 1. So as I mentioned, we have to use node number and element number, because stiffness method is the theory behind the software. Of course, we can label as ABC as usual, but we want you to be more familiar with stiffness method. We need to put numbering, okay, to represent nodes and element. And in this diagram, we can see that nodes represent by number in the circle. Okay, this is node. This is node. Node represent by number in the circle. This is node 1. We have node 2 here. We have node 3. And we have node number 4. Okay, and we have element number. Remember, element joining two nodes means that for element number 1, joining node number 1 to node number 2, an element representing by number in the square box. Okay. The near and far end of each element are identified by the arrows written alongside each element. So we can see that this is the arrow. Okay, actually when we analyze beam, we whether then we put the arrow or not, we can assume that the direction is always going to the right side. Okay, to the right side. And how do we identify near and far end condition? How? So how? So it will always going to the far end. The arrow always going to the far end. So this one will become near Okay, and arrow is going to far end. So we have to understand which is the near end, which is the far end. Okay. So for the global and member coordinates, okay, since beam has the same local coordinate system and global coordinate system, so we have the same formula. We have the same formula, but remember that for the global system, we use the symbol without prime. We use the symbol without prime. Okay, before we move to okay, the example. Okay, let's understand about the kinematic indeterminacy first. Okay, once the element and nodes have been identified and the global coordinate system has been established, the degree of freedom for the beam and its kinematic determinacy can be determined. Okay, consider both bending and shear, then each node of a beam can have two degree of freedom, namely vertical displacement and rotation. Okay, because the definition is of degree of freedom itself, in simple word means that it is displacement component. So this y and z in terms of displacement, it represent the vertical displacement as well as rotation. Okay, as well as rotation. And one important thing is the lowest code number will use to identify the unknown displacement, and it will be put in unconstrained degree of freedom. Means that we need to label the unconstrained system first, followed by constrained system. Means that whenever we have the structure, we get the structure, what we need to do first is we have to sketch two system. One is unconstrained system, another one is constrained system, and we will label the degree of freedom separately between unconstrained and constrained system. Okay. Okay, so this is actually how we get the formula, and this formula normally will be given. Okay, will be given in test or in final exam. Okay, and during this MCO, you can also refer formula directly. Okay, during your test. Okay, sign convention. Okay, sign convention. Okay, by looking at this, y is upward and z is counterclockwise. Same for both near and far nodes. So we have to refer to this. We have to use this as sign convention, because this formula is derived based on this direction. Means that we cannot simply change the direction. Okay, so finally, this is the formula. It is K. Okay, the stiffness matrix, the stiffness is K. Okay, and in stiffness method, we will return all in matrix form. So it will call as stiffness matrix. And this is actually the member stiffness matrix or stiffness matrix for stiffness matrix for element. So it has four by four here, 4 by 4 here. Why it has 4 by 4? Because in one element we have near node, we have far node, and each node we have two. Each node we have two. So there are 2 degree of freedom per node. 2 degree of freedom per node. So this actually we can label if this is yz. So this is the position. The position inside the matrix is near y, near z. Okay, the first two is for the near node, and the last two is for the far y, far z. Okay. Okay, so beam structure stiffness matrix. The structure stiffness matrix will be assembled once all the member stiffness matrices have been established. Means that we need to start from node. Start from node, we establish the member stiffness matrices or the element global stiffness matrices, and from that we establish the structure stiffness matrix. Okay, remember we analyze the structure by analyzing, by we subdivide the structure into element, means to get back the structure for the K for the structure, the stiffness metric for the structure, we have to start from member, and from member we will combine back to have the structure stiffness matrix. So the small letter is for the element, the small letter is for the element, and the capital letter will be used for the structure. So the small letter is for element. So let's say there are two elements, element 1 and element 2. So there will be K1, K1 and K2. And to have the structure stiffness matrix, we will combine, this is capital, equal to K1 plus K2. And total degree of freedom will be based on node number, will be based on node number. Okay, if there are 3 nodes, means there are 6 by 6 matrix in the structure stiffness matrix K. Okay, and K we have to label in order. Okay, K for the capital K, or for the structure stiffness matrix, we have to label in order from, okay, from 1 to the highest code number, this one. Okay, to represent the total number of degree of freedom. Okay, so we now move to application of stiffness method for beam analysis. So we have this as the force displacement equation, and it will be divided into QK and QU. So K and U representing unconstrained and constrained system. Unconstrained and constrained system. Okay. Okay, then we need to understand also intermediate loading. Intermediate loading. Okay, this is actually you have, if you are coming from matriculasi, this is new to you. But if you are coming from diploma, actually you have used this in analysis of beam using moment distribution method. This is actually called as fixed end moment. Fixed end, fixed end moment. Fixed end moment. Fixed end moment means we assume that both end is fixed. Both end is fixed, and whenever the beam is subjected to any type of load on the beam. Okay, on the beam. It may be along the beam, UDL along the beam, or it may be point load at the center, or it may be the point load at anywhere along the beam, but not at joint. Not not at joint. It is just for calculating or to distributing the member load to the nodes. Okay, in intermediate loading, what we need to do, what we need to understand is, because in stiffness matrix method itself, we only analyze the displacement and forces at nodes. So when we have intermediate loading, what we need to do is we have to divide the loading, okay, or not divide, we have to distribute. We have to distribute the loading to the nodes. We have to distribute the loading to the nodes by using the formula. By using the formula, it is called as fixed end reaction. Okay, basically, when both end is fixed, there are moment at both end, and to balance back, there is also the vertical reaction. Vertical reaction. Okay, so this condition we require modification. Okay, we have to apply fixed end moment and reaction to the element. Okay, so this is the formula, the very regular formula. So actually, in the appendix, in the final exam, normally you will be given up to 8 formula for fixed and action. But basically, in the analysis, we normally have these 4 type of loading. Okay, given to you in test or final exam. Okay, final exam. So this is the regular type of intermediate loading. Number one, this is number one when there is a beam. Okay, we put the fix at both end, or we assume both end is fixed. In this analysis, for the beam analysis, doesn't matter. We have to put or to assume both end is fixed. Okay, so by having this, so the formula to calculate fixed end moment, MA and MB, okay, is this WS square over 12, and for the vertical forces is WL over 2. Okay, and number 2 is triangular load. Number 3 is point load at the center of the beam, and number 4 is point load not at the center. So these are the formula to use. Okay, and remember that for fixed and action, and action, this is not the sign convention. Okay, this is not assumption. No, what I mean is this is not assumption. That this direction, okay, this direction we put like that. That is not because of we assume the direction. This fixed end action or fixed end moment is actually behavior. Is actually behavior like this. When we have beam, okay, we apply load. What happened to this? It will bend. It will bend due to the loading on top of it. So basically the beam will bend. So what is the function of the fixed end action or fixed end moment? Okay, to balance back. So in order to balance back, in order to push back the bend beam to its original position, what we need to do is we have to apply moment in this direction so that it can go back to straight position. It can go back to straight position like this. Okay, like this. That is why we have this direction. Okay, because we have to apply moment in order to counter back the beam to its original position. Okay, same goes to the shear force. So to balance back, we have to apply in opposite direction. So that is why we have this in the formula. Okay, so we move to the procedure for analysis. We have, okay, for the notation, we need to divide the beam into element and identify nodes. So I hope everyone understand about this. Okay, A and I. A and I in the software, it is called as section properties. Okay, in the software, this A and I is section properties. Section properties. Section properties. Okay, and we need to specify near and far end. Okay, near and far end means nodes. Remember that we have to analyze, start from node, node produce element produce structure. So we have to do the analysis backward. Okay, and then we need to label. When we want to label, we need to label unconstrained first. Unconstrained first, followed by constraint. Unconstrained first, followed by constraint. Because in unconstrained, there are unknown displacement, and we will use this unknown displacement, okay, to analyze the reaction at the support. Okay, the structure stiffness matrix, we apply beam element formula to establish the stiffness matrix for each element expressed in global coordinate. Note that the element and structure stiffness matrices should be symmetric. So the characteristic of the matrix, okay, we use in this topic. Okay, so the matrix that we produce, whether it is element stiffness matrix or structure stiffness matrix, we always symmetry. And lastly, we have to put to write the displacement in matrix, the load in matrix, displacement and load in matrix, and we will write the force displacement equation. And after that, we will solve for the unknown displacement as the first output. Then only we can determine the reaction. Unknown displacement first, followed by unknown reaction. Okay, so we will continue to see the example and solution. Okay, let's look at this example together. Okay, this figure in example 1, figure 5 in example 1. Okay, figure 5 shows an indeterminate beam having 3 nodes and 2 elements. Okay, the beam is fixed at node number 1, whereas node number 2 and node number 3 are pinned. Okay, so every time you must read the question carefully. Okay, node number 1 is fixed, node number 2 and node number 3 are pinned. EI constant, and element number 1 is subjected to 30 kilonewton vertical load as shown. Okay, let's look at the question. And actually, by looking at this question here, it is just like it is actually the procedure step by step. Number 1, we need to establish element global stiffness matrices. Okay, from nodes. Okay, and then we establish this element global stiffness matrices. This is K1 and K2 because in this beam there are 2 elements. So we will produce K1 and K2. K, K2, K1 and K2 using the formula given in appendix, where the stiffness matrix is 4 by 4 matrix because there are each element has 2 nodes and each node has 2 degrees of freedom. So for element stiffness matrix, we will get 4 by 4 matrix. We will get K1 4 by 4, K2 also 4 by 4. And after that, we will establish the structure stiffness matrix. The structure stiffness matrix. The first one is element. The first one is element. The second one is structure stiffness matrix. Structure stiffness matrix, capital K equal to K1 plus K2. And there are 3 nodes. So 3 times 2 is 6. So we will get K. Okay, K. The stiffness matrix for the structure stiffness matrix is 6 by 6. Okay, step number 2 or question number 2. We need to establish the element equivalent nodal forces and equivalent nodal forces. This one is actually, okay, what is this? What is this? This is actually called as intermediate loading. Intermediate loading. So when we analyze beam, normally in normal case, there will be intermediate loading. For example, in this case, this 30 kilonewton subjected at the center. Okay, at the center of element number 1. So this one we need to analyze using fixed end action that I have explained to you just now. Okay, then only we can form the stiffness equation for the beam and solve for the unknown displacement. Okay, solve for the unknown displacement in unconstrained system. Okay, number 4. This is number 4. The first output, the first output, and number 5 is the second output, which is unknown reaction. Okay, let's look at one by one. Okay, this is the 2 system that I have mentioned. Every time we want to start analyze beam using stiffness method, we need to separate between unconstrained system and constrained system. Remember that constraint represents support. So, and the easiest way to identify number of degree of freedom in constrained system is by referring to number of unknown reaction in the beam. Number of unknown reaction in the beam. So this beam is like this, fixed pin pin, fixed pin pin. Okay, conventionally, so just look at this conventionally previously in solid mechanics, indeterminate structure, when we have the beam, we will draw the free body diagram and we will put the direction, okay, of reaction of unknown reaction at each support. So at note number 1, this is fixed. We have, this is conventional. Okay, X, Y, Z. This is X and Y. This is X and Y. But remember, in the stiffness method, we only count Y and Z. Okay, doesn't matter with this direction, because this is just the common way we put the reaction at the support. So remember that this is the sign convention. This is sign convention that we need to refer. The sign convention that we need to refer, we have to count only 2 degree of freedom. Means that we do not count the X direction. Means we will not count this. We will not count this. Okay. Okay, we will not count this, and we also not count this. So we have two at node number 1, we have 1 at node number 2, and we have 1 at node number 3. So total is 4 degree of freedom in constraint system. 4 degree of freedom in constraint system. So we have to put the degree of freedom, this degree of freedom. Okay, there are 2 at node number 1 in Y and Z, must be clockwise, must be counterclockwise, and we have 1 at node number 2, and another one is located at node number 3. This is actually representing the unknown reaction in the system. And please remember that since there are 3 nodes, so the total must be 6. The total must be 6, and each node must have 2 degree of freedom. So the remaining two must be put in the other system. Okay, so at node number 1, there are no more DOF to put, because there are 2 in the constraint system. Okay, at node number 2, since in constraint system there is only Y, so means that Z will be put in unconstrained system. And another one, okay, there is Y located at constraint, so the other one is Z located in unconstrained system. Total must be 6. Total must be 6, and it must be YZ, YZ, YZ. So when we label, we need to label the unconstrained system first. Unconstrained system first. So we have to put 1 and 2 in unconstrained system. Then only we followed by 3, 4, 5, 6 in constrained system. The reason to do this is because, as I mentioned to you, the displacement, the unknown displacement is the first objective, is the first outcome, and we will actually use this unknown displacement in order to calculate the unknown reaction in constraint system. Means that when we do not, when we don't know the value of unknown displacement, we cannot determine the unknown reaction. We must determine the unknown displacement first. Okay, so move to the next one, the next slide. Okay, so we need to establish the global stiffness matrices. Why I use the word global? Because we are referring to the coordinate system in the analysis of structure using stiffness method, whether it is truss structure or beam structure or or frame structure, we have to refer to the global coordinate system. So what we need to do is we have to refer to the formula given in appendix. Formula given in appendix, okay, and using the formula, and in terms of EI, okay, we have to have the stiffness metric like this. Okay, like this. So the most important part is how we label this. So this will depend on the degree of freedom for the element. So for K1 and K2 is for element. Remember that I have mentioned just now, it is near, the first two is for near end. The first two is for near end. The last two is for the far end. And at each node, there are YZ, YZ. So that is why the label is 5642. Refer back to the previous one. Okay, it is 56. Okay, 56 YZ 42. 56 YZ 42 YZ. So that is why the label is 5642. 5642 for both. Okay, for both vertical and horizontal label. 5642. Okay, for both. Okay, and for K2 is for element number 2, and element number 2, the label YZ is 4231. 4231. So 4231 is, okay, 4231. 4231. Okay, so by having these two stiffness matrix for element, we will combine to produce the structure stiffness matrix. Okay, we will combine to produce the structure stiffness matrix. But remember, the structure stiffness matrix must be written in order. In order means from 1 to 6. So this is actually the label inside the member stiffness matrices is actually the position in the structure stiffness matrix. So this is number 1. This is number 1, number 2, number 3, number 4, number 5, number 6. Okay. So what we need to do now is just to combine. Combine means that when we want to determine the value at position 1, 1, so we have to find where is the value in K1 and K2 representing 1, 1. Representing 1, 1. Where is the value? Okay, where is the value? 1, 1 is 1.6. 1, 1 is 1.6. Okay, then 1, 2 or 2, 1. 1, 2 or 2, 1, it is 0.8. And then 1, 3. 1, 3, 3, 1, it is negative 0.96. So we will do the same until we get all the value. And I just write like this because, as I mentioned, the characteristic of the matrix must be symmetry. So we can always write like this. Okay, 6, 6. 6, 6, we have 6, 6, 6. So it is 0.8. So this is 0.8. Okay, so once we have all these structure stiffness matrix, then only we move to analysis of intermediate forces. It is called as element equivalent nodal forces. Element equivalent nodal forces. So same with K, we need to analyze element first, then only we can combine to have the structure stiffness matrix. So when we want to analyze the intermediate loading, we need to analyze element by element. Start with element number 1 followed by element number 2. And for the label, we will use the same label. So the same label that we use in K1 and K2. For example, we use for K1, we use the label as 5642 and 4231. So we will use again in the analysis of element equivalent nodal forces. Okay, so for the label, remember, for the equivalent element nodal forces or element equivalent nodal forces, it is nodal forces. Nodal forces. It has the word equivalent. Okay, equivalent nodal forces to differentiate between nodal forces that you have learned in the structure in the truss structure. Okay, we use Q for nodal forces, but now we have equivalent nodal forces, so we use the symbol Q naught. Q naught. So you can see that this is Q naught and Q naught. So numbering 1 and 2 representing member number 1 and member number 2, or element number 1 and element number 2. So we have to just to refer back to the formula. Okay, formula. So P at the center. So to balance back or to get equilibrium condition, P must be P over 2 and P over 2. So that, okay, it will be balanced. And for the moment also, the sign convention, as I mentioned, due to beam like this, okay, we have to apply moment to push back the beam to its original position. So that is why the direction is like this and like this. And then we just have to apply the formula PL over 8. Okay, PL over 8. And the most important part is we normally compare the formula and the sign convention. Okay, formula and the sign convention like this. Okay, okay. Formula and the sign convention. So what we need to do is, okay, compare these two. Okay, so we have 5, 6, 4, 2. 5, 6, 4, 2. So for 5, 5 is equivalent to P over 2. Okay, 6 is equivalent to PL over 8. If it has same direction of moment, it represent positive. Okay, and for okay, here P over 2 is for node number 4. Uh, that is not degree of freedom number 4. And the moment, okay, at the moment here, okay, this is the moment. This moment we compare to this moment. Okay, it is opposite means negative. So we have like this. Okay, so the value is this one. The value is this one negative, representing degree of freedom number 2. Okay, degree of freedom number 2, it is negative. The rest is all positive. So same direction positive, different direction or opposite direction is negative. And for element number 2, since there is no load on top of the member, so all the value is 0. Okay, so we combine these two, Q10 and Q20 like this. Okay, Q10 and Q20 like this. Remember that this label, okay, this label, okay, remember that this label and this label is actually the position in the structure. So when we combine to have the equivalent nodal forces, okay, this one is written in order just like K from 1 to 6. And if we want to calculate the value at position 1, we just have to refer back to this. Where is 1 in Q10 and Q20? The value is 0. And then at position number 2, it is negative 18.75 here. Okay, at position 3, it is 0. At position 4, 15 plus 0 at position 5. Position 5, 15. Position 6, 18.75, 18.75. So this is called as equivalent nodal forces or intermediate loading. Okay, so in order to solve for the unknown displacement, we also have to write the nodal forces Q as well as nodal displacement, all must be written in matrix form. And here is why we have to refer back to have the unconstrained and constrained system. Remember that in the diagram that we sketch, in the first place, okay, in the constraint system, there are 2 degree of freedom, and in constraint system, there are 4 degree of freedom. So it representing this. Okay, so for Q, we will have Q1 until Q6. So the unknown reaction, okay, are located in constraint system start from Q3 until Q6. And for the unknown displacement, we have D1 and D2 located in unconstrained system. So D3 until D6 is equal to 0 because of the support. And logically, the support at support displacements are 0 except when there is a support settlement mentioned in the question. Okay, so all this Q naught, Q and D will be written or will be put into the equation, force displacement equation, or we also call it as structure stiffness equation. Okay, from 1 to 6, this is Q, this is K. In terms of EI, D and Q naught. And we will analyze this using multiplication, using matrix multiplication. And since here is 0, 0, 0, 0, so what we actually do is we only analyze this, this, and this. That is why I simplify this big equation of stiffness equation into the structure stiffness equation corresponding to unconstrained degree of freedom. Okay, so by having this one, okay, by having this one, so we have actually two simultaneous equation, and we can solve this using calculator. Okay, so we rearrange this and we will have the answer like this. Okay, D1 and D2. In terms of EI, if we don't have EI value, if we have EI value, then we will get displacement. And in this case, displacement represent rotation because it represent this and this. This is 1, this is 2. It represent rotation. Okay, rotation at node number 2 and node number 3. It actually representing this. This is spin. This is spin. Okay. Representing this. Okay. Representing what? Representing this. This is actually D2. And this is actually D1. Okay. It represent rotation. Why it is rotation? Because it is Z. Z is for rotation. Okay. Rotation. Okay. So we get displacement like this. And once we have this displacement, to calculate or to complete this analysis, we will substitute into the stiffness equation. So these two displacement, we will put into the big one, this equation. Okay, put D1 and D2 here. Okay, D1 and D2 that we get. Okay, after we have solved the two simultaneous equation, we get this value. So this value we have to put back into the big stiffness equation, and we will analyze the reaction at the support using multiplication. This is just mathematical calculation. I hope you know how to analyze this. And finally, we will get the Q3, Q4, Q5, Q6 using multiplication, and we get the reaction at the support as this. Okay, as this. So I hope that everyone understand the flow the procedure, the concept of beam analysis using stiffness method. Actually, when we have this reaction at the support, we can put back into the beam, into the beam. We can put into the beam. Okay, pin here, pin here. So we have the 30, and we can refer back to the label that we use, 3, 4, 5, 6, and we can put all the reaction into this one. For example, refer back 3, where is 3? So refer back 3 is, if I'm not mistaken, 3 is Y, means 3 Y. Okay, this is 3, 3, 4, 5, 6. So 3 means okay, 3 means 4.5 negative. So it means that this one 4.5 kilonewton. Kilonewton. 4 is negative. It is also negative. Negative 16.5. We don't have to put negative. The direction represent negative. 16.5 kilonewton. Okay, 16.5 kilonewton. Q5, 5 is also Y direction. This is 2.25. And moment is counterclockwise, 18.75. So, having this, we can actually check for equilibrium. We can check for equilibrium using equilibrium equation. Okay, using equilibrium equation, we check whether we will get this total M is equal to 0, total Fy is equal to 0, and total Fx, of course, this one is equal to 0. Okay, when all this fulfilled, then we can be able to draw the shear force diagram and the bending moment diagram. We draw shear force diagram and bending moment diagram. After we have checked this, and we have to make sure that all this is fulfilled. Okay, means that the diagram must be closed loop. Okay. In the next session, maybe I will focus on how to draw the shear force diagram and bending moment diagram without having cutting section like what you have done under solid mechanic. From this, okay, from this, all the values that we calculate using stiffness method, we will close with shear force diagram and bending moment diagram. I will show to you in the next video. So I hope you understand this. If you don't understand, please contact me and I will explain to you again. Okay, thank you very much. And Assalamualaikum warahmatullahi wabarakatuh. Okay, bye. Okay, so I hope everyone understand, and we will meet again in the next session. Okay, bye.